Hello. So today we are going to talk about prophecy and attenuation. This is the last little chunk. Can I help you, Dukes? Okay. Well, sorry, we don't have a celebrity guest. I'll see if I can summon him because I know that there have been a dearth of cats in the most recent videos. And some of you like that. Or not the dearth, you like cats. So yeah, let's talk about prophecy and attenuation. Ooh, 1 second. Oh, apparently we're at the top. Great. Well, yes, this is just life today. Cool. Here, move. There we go. Okay. Cool. Enjoy that awkwardness. But anyway, let's talk about prophecy and attenuation. So, a question that you've probably asked yourself many, many times, all the time, constantly, is how much reliability do we want? No? You haven't asked that? That's okay. I was kidding, in case that was unclear. Typically, we want a value above 0.8. So what happens if we don't have that? Well, the Spearman-Brown formula, our trusty friend, can be algebraically manipulated to achieve that. So we can see J is the number of tests at the current length, and our desired reliability is R sub D, and our observed reliability is R sub O. So we can pop in those numbers to figure out how much longer our test needs to be in order to get the reliability we want. To illustrate, I have our favorite 3 items that have a really nice reliability of almost 0.9. So what happens if we want to increase that to 0.95? Well, we pop those numbers into our handy dandy equation here. As we can see, so our goal reliability is 0.95. So we put that in. Okay, apparently my mouse capture is not gonna make a difference here. So what we can do is pop in that reliability of 0.95 in R equals D and multiply that by the difference between 1 and our error. So the 1 minus the proportion of variance explained. So it's our reliability times the proportion of variance left unexplained. And then we divide that by our current variance, our current alpha, R0, so just under 0.9. And then we multiply that by the difference between 1 and what we want our reliability to be. And we pop those numbers in. You are welcome to do this in R. It will save you a lot of math later. I don't do any hand calculations anymore, and I get R to do them for me. It's lovely. But what we do is we divide the top by the bottom, so 0.09-ish divided by 0.04-ish, and that gives us 2.2. So we need a test 2 1/5 times longer than the original. So 3 times 2 and a smidge is almost 7. And so it's probably safe to just round up to 7. So we would need this test to more than double in length to give us that reliability that we want. Cool. So now let's talk about correction for attenuation. So correlations are typically sought at the true score level, but the presence of measurement error can cloud or attenuate the effect size, that estimate. And so we can correct for the size of the correlation when we have a low reliability of items. And to do this, I've got an equation on the next slide, but this is kind of a last resort if you don't have a means to actually collect more data. This can be a way to get a sense of what that correlation would be if you had a more reliable test. And you can calculate that correction for attenuation by having the correlation between, or the reliability for test one. I cannot read. Sorry. So we can calculate here using R hat is our corrected correlation. Hat is an estimate. That's the little hat thing for those of you who didn't cover that in 312. But yeah, so R hat is our end result, and what we put in there is the original uncorrected correlation. That's in the top. That's R sub 1, 2, as well as the known reliabilities for our two tests. So if we already know that their reliability is dicey, um, and you should be estimating this from ideally pre-existing measures, not using the reliability of your measure of your data right now. But yeah, so we pop those two in, and our end result is what we would expect our correlation to be if we had had, well, perfectly reliable measures. So for example, say X and Y are correlated at 0.45, and the reliability of X on the scale has a reliability of 0.8, while Y has a reliability of 0.6. We can pop all those numbers in, as I've illustrated here. I encourage you to practice doing this in R. And we can see that once we adjust for our attenuation for our unreliability, we can see that our actual correlation is projected to be 0.65. That is a bump from a medium effect to a larger effect. And that's my alarm. Hey, Google. Hey, Google. Quiet. Cool. Yeah, well, we were so close to making the time. So, that is wrapping up prophecy and attenuation in this entire module. There's a reason why I keep harping on Spearman Brown, because it's super useful. We use it all the time. So, be able to use it. Cool. So, I'll see you all later. Bye.